Alright, we're back in section 8.2, so we're going to look at some visualizations of functions of two variables. So these are called contour diagrams. So contour diagrams allow us to look at functions of two variables in two dimensions, even though functions of two variables usually give us information about 3D surfaces. So we have, right, in functions of a single variable, right, you have the x-axis, you have the y-axis, I get my x-coordinate, my y-coordinate, I plot a point, right, and then you look at a graph on those coordinates there. For functions of two variables, well, now you have the inputs of x and y, so x input, y input, but that gives you now a third variable as an output. Typically we call it z. You're not going to need to worry too much about that, but we would typically draw it like this, where that's x, that's y, and that's z. Okay, and then we get the x-coordinate, the y-coordinate, and the output coordinate z. You can just kind of visualize, tracing this point up until it hits that coordinate there. Right, and then we can look at 3D surfaces and curves using functions of two variables. But typically we don't want to have to work with 3D graphing, so we're going to use contour maps and contour diagrams to be able to describe the behavior of a function of two variables. So common examples of contour diagrams are weather maps and topographical maps. So you can see here a topographical map of just some region, right, some mountainous region. The idea behind the contour diagram is each curve on the contour diagram represents a different height. Okay, so if you look on this contour diagram, for example, this one right here, this contour, notice it says 550 on it, so that means anywhere along this contour has a height of 550 all the way along there. Okay, and then this one looks like it's going up by tens, so this one would be 560, 570, 580, 590, 600 here. So that has a height of 600 all the way around there. Okay, so we can use these contours to visualize a 3D object using just a 2D graph. And you can see here we going from 550 up to 600 to 650 all the way up to 682.5. Notice this is a point here instead of a curve. That's because that is a single highest point. So you might be able to tell by looking at this, but this is actually a mountain. So notice it goes right here and then it starts getting wider and wider like that. These contours are pretty close together because it's growing pretty steeply, right? If I have two contours that are like, if you look on the right side here, two contours that are like that, and this tells me, that's 560 and that's 590 or whatever. Okay, that tells me I just went up 30 feet over this distance here. Whereas if you tell me that these two contours, that one's 560 and that one's 590, then this tells me I had to go this far in order to cover 30 feet in altitude. Okay, so this would represent very steep increase. This is very shallow increase. Right, so very low slope. Okay, so this is what contour diagrams can do for us. They allow us to look at 3D surfaces on a 2D plane, right, on a piece of paper, basically, instead of having to draw them out in 3D. So have a lot of practical applications here. Okay, so now every point along the same contour. This is what I kind of was just talking about. Contours are also called level curves. So if you hear me saying level curves, that's what I'm talking about. Has the same elevation. And the closer the contours, the steeper the terrain, the further apart the contours, the flatter the terrain. Okay, so with these examples down here, these are all contour maps, contour diagrams, and I'm going to do my best to show you guys what the equivalent 3D surface would look like for each of these. So we're going to start with this first one here. So We have 300, 400, 500 as we're getting in towards the middle. So these are all circular. So I'm going to draw a little bit of perspective here. But there's our top one. 400 is going to be out just a little bit further like that. Oops, a little too far. Something like that. And then 300 is a little bit wider than that one. Something like that. And I'm going to connect those. So this would look something almost like a volcano, a hill or something with a flat top. It could go on higher than that. But this is 500, 400, and 300. So if you just visualize in terms of like feet, so we have 500 feet, 400 feet, and 300 feet. Okay, and obviously we have other values besides those if we just kept going. But if you're wondering how this translates to the contour diagram up here, how they relate, well, if you just trace, do this in a different color, trace this down. So imagine that the ground is down here somewhere. Just go straight down with all of these shapes. Okay. And then we'll see here there are the circles down there. So if you just kind of visualize, right, projecting these down on the ground, you can see that they create those circles, which are these circles up here. Okay. So that's our first one. I know visualizing the 3D can be challenging. So if you're having trouble with it, let me know. But this is just to give you an idea. We're not going to do a lot of 3D drawing in here. Just reading and interpreting the contour diagrams. So let's look at the second one here. So this one's kind of interesting. So notice we have this pattern. It's increasing as we go out to the left and right, but it's decreasing as we go up and down here. So to get a clear picture of what's going on here, let's go ahead and so I'll draw my 800s. So those are going to be somewhere like here and here. And then my 300s, I'm going to put, it's going to be down here. Oops. So down here. And then for perspective, I'm going to put this one way down there. Okay, and then the 600. So let me just put a little perspective on that. Okay. There we go. So if you can see what's going on here, so here's 800, 700, or sorry, that one's 600. This one's 800, 700. That one should be a little higher up than the other one. Okay, this is 500, 300, 500, 300. Okay, so if you can kind of visualize what's happening here on this shape, this looks kind of like a saddle, right? So just picture like riding a horse. So with the front being here, maybe the back being here, and then like these sides are hanging over, right? The side of the horse because it's going down there, and you would sit right here, kind of on the little indent in the middle of the saddle. Okay, that's kind of what's going on here with this one. These ones are a little bit harder to draw, but hopefully you're getting kind of the idea of what this looks like, right? So we have it's got kind of this curve to it, right? So if we are standing on the top here, right, we're going down, we go down that way, we go up this way, up this way. So hopefully that's pretty clear. Okay, and then this one. So we have 200, 100, 100, 200. So that's going to be just straight lines. So let me put the 200s in first. So 200 and 200, and then it's going to dip. Oops. As you can see, drawing these is not the easiest thing in the world. And down there, and down there, that's going to be 100 and 100. Okay, so this one, the contours are evenly spaced, right? So it has kind of the same length, same distance from here to here, here to here, and then here to here on all of those. Oops. So this one, you get kind of this shape going on there, like if you were to fold a piece of paper, right, and just kind of hold it, kind of fold it a little bit. Okay, and then this last one, we have a contour of 100, a contour of 200. Now this one is interesting because this one tells me everything along this contour has a height of 100. Everything along this contour has a height of 200. The problem is right here in the middle where they meet. For somehow that point in the middle is supposed to have a height of 100 and 200 simultaneously, and that is not possible. So this one is actually not possible. This is not a valid contour diagram. So contours of different heights should never intersect each other. Okay, you can have contours of the same height intersecting each other, but contours of different heights should never intersect because that gives you a contradiction like this, where somehow this point is supposed to be, 100 high and 200 high at the same time, and that just doesn't work. If they did something like this, where you had a contour of 100 on both sides and then like 200 on both sides like this, and then something kind of weird in the middle like a 150, all of which are not intersecting, then you could have a different conversation about what that looks like. But you can't have contours of different heights intersecting each other. Okay, so that's kind of our introduction to visualizing these contours. So now let's look at some interpretation of these contour diagrams. So here we have a function of r and t. This represents corn production, where r is rainfall in inches and t is temperature in degrees Fahrenheit. Evaluate and explain f of 18,78 and f of 12,76. Okay, so for f of 18,78, so in this case, we have two inputs and we're getting an output. So one input is given along the x-axis, one is given along the y-axis. The contour values in here, those represent the heights. Those represent the output values. Okay, so again, input, the contours are giving me the outputs. All right, so let's look at the graph. We're looking at the point 1878. So 18 is right here, 78 is right here. If we track those two, we see they intersect right there. And that does lie along one of the contours, right? That lies perfectly on the contour at 100. Right? So that's on the 100 contour. So that tells me that that is the output. Okay, so the output value for these is 100. All right, so now what does this tell us? Well, if you look back at the original here, so this is f of r comma t. So r is rainfall, t is temperature. So in this case, we have r is 18, t is 78, and c, the output, is 100. So if rainfall is 18 inches and temperature is 78 degrees, corn production would be 100 units. In whatever the units are of corn production. Okay, so that would be what we get for that function. Okay, so now let's look at the other one they asked us about. So this is f of 1276. So for this one, so here's 12, here's 76. So if we go right there, so that's our point right there. Now, this point does not lie on a contour. So we can't just easily say, oh, it's got to be 100 like we did on the last one. But if you notice, it lies kind of directly between two contours, right? Between the 80 contour and the 90 contour. So we can actually use that and say that this one is somewhere between 80 and 90. It looks like it's about halfway, right? Maybe not exactly, but we're just approximating here. So I would say that the value would be about 85. Okay, about halfway between the 80 and 90 contours. So this is going to be approximately 85. And again, this is between the 80 and 90 contours. So again, let's interpret what this statement means. So it says at 12 inches of rainfall and 76 degrees, corn production is approximately 85 units. So notice this is less than the other case. Okay, so we can use models like this to look at output values, right? So in this case, corn production, based on multiple input values, right? Because the temperature alone does not determine how much corn you produce, and also the rain alone does not determine how much corn you produce. It's a factor of both. So we can look at functions of two variables like this and visualize them, and that allows us to look at more specific values and make interpretations, and then hopefully make decisions about what we should do. Okay, so let's look at one more. So finding contours algebraically. So find f of xy equals c, where c is constant. So this is how we're going to find contours. You take the function, you set it equal to a constant, and when you set it equal to a constant, that gives you one level curve. Okay, so like for example, in this previous example here, We had the function. When you set it equal to 40, it gives you this curve. When you set it equal to 50, it gives you this one. 60 is this one. 70, 80, 90, 100, 110, 113, etc. Okay? So setting it equal to a constant gives you that 2D graph, right? This graph on the xy plane. So let's try that. So draw a contour diagram for the airline revenue function, r equals 350x plus 200y. Include contours for 4,000, 8,000, 12,000, and 16,000. So let's do that here. Let me actually just type this part in. So r equals 4,000. Oops. R equals 8,000. R equals 12,000. And R equals 16,000. So there we go. We can just take the function, set it equal to that value of r, so we get 350x plus 200y equals 4,000. Solve that for the equation in terms of, right, y equals. So y equals, if we subtract the 350x over to the other side, divide both sides by 200, we're going to get negative 7/4 x plus 20. Oops. And then we just keep doing that same thing. So 350x plus 200y equals 8,000. Subtract the 350x over, divide by the 200. We get y equals negative 7/4 x plus 40. Okay, when r is 12,000, we get the function y equals negative 7/4 x plus 60. And then when r is 16,000, again solving for y, we get negative 7/4 x plus 80. So notice that the slope, this is the equation of a line, right? Y equals mx plus b. The slope of each of these lines is the same, right? Negative 7/4. That's because it's based on the 350 and the 200, so that's not going to change. The only value that's changing here is the y-intercept, 20, 40, 60, 80, is increasing as the value of r increases. Okay, so we're going to get lines that are parallel because they have the same slope and just have different y-intercepts. So, right, if we just graph this here, so we've got x, we've got y, 20, 40, 60, 80, and a slope of negative 7/4, you get something that looks kind of like that. So that would be what this contour diagram looks like with all these different level curves, right? So this is 4,000, 8,000, 12,000, and 16,000. Okay. So I do want to show you guys how we can do this on Desmos, and then I'm going to give you a better visual here. So let's switch over. Okay, so to set up the contours, so we're going to go ahead and punch in the equation. So 350x plus 200y equals whatever variable you want. So in this case it was capital R. Now, it'll ask you if you want to add a slider for R. We don't want to add a slider in this case. We actually want to pick specific values of R, and that's what we're doing, right? We set it equal to a constant. So we're going to pick R equals, and then I'm going to use the square bracket because that tells it I want a list, 4,000 and 8,000 and 12,000 and 16,000, and then close that out. And then let's go take a look, and there they are. Okay, and I can even restrict this further. I could go ahead and just restrict my values to be, that's okay, I won't add restriction to it. So, but this is what we get. So these are the contours, right? And it doesn't matter what the contour values are. I could pick something as small as, 1. Add that on there so you can see that way down here. Right? So it can be any value you want. You could even put a negative number in there. So as that starts moving down towards the negatives, and that would be fine. Nothing wrong with that either. So it's just in this case we specifically were looking at those 4. Okay, so but it gives us those 4 lines. Okay, now visualizing this graphically, so we saw one just like this earlier, right? So it gave us kind of a swoop, like a parabolic shape to it. Let me show you guys, except this time they're only strictly increasing or decreasing. So let me pull this up. This is not something you guys are going to need to be able to do. I just have the coding for it. If I can find it, here we go. So here I have, this is a different graph that we might work with at some point. But let me just get rid of this. So we have 350x plus 200y. Okay, now this may not look like much right now, but let me rotate this a little bit so you can see. So if you can kind of get the picture here of what's happening, we have a very flat surface. It's very steep, right? But when I look at it from this perspective, we're almost right in line with it here, right? So I'm getting this, what this is called a plane. So it's flat. So just picture kind of holding up, right, a flat surface like a, piece of wood, a piece of paper, like something long and flat, holding it up, kind of cutting through the axes like that. That's the shape that we have here. Okay, so it's giving us a plane, just a nice flat surface. And that's kind of what we have going on here. But the contour diagram really is the most descriptive part of that. So this gives us more information, being able to look at these values here instead of having to look at that 3D graph and interpret what it's saying. Okay. All right, so that brings us to the end of section 8.2. So that's it for today. When we come back next time, we're going to start looking at more of the calculus of functions of two variables. So we'll get into that next time.